Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science, uh, and my courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, and so guys, this is the lecture number 22 of condensed matter physics, okay, in which I'm going to discuss magnetism in solid, and this is the last lecture, and then the solid state, this condensed matter physics is going to be completed. Okay, so and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, and also guys, please share my lecture details to your friends so that your friends can also be able to watch my free live lectures and will be benefited from it. Okay, so let's get started. Okay, so magnetism in solid. Okay, magnetism in solid. So we are going to study magnetism in solid. Meanwhile, just let me check whether I'm audible or not. Then I'll proceed further. Okay, so let's get started. Yes, I'm audible, so I'll proceed further. Okay, so first diamagnetism, guys. Okay, diamagnetism, dia diamagnetism, diamagnetism. Okay, diamagnetism. So in diamagnetism, guys, mu r, that relative permeability is equal to chi plus 1. Okay, this is important. Diamagnetism, I have also explained in superconductivity in my previous lecture. Okay, so I'll write some points. Okay, so in absence, okay, so I'm talking about diamagnetic substances. Okay, so in absence of magnetic field, in absence of magnetic field, okay, in absence of magnetic field, all the dipoles all the dipoles all the dipoles are are randomly arranged randomly arranged. Okay, okay, so if we talk about those diamagnetic substance, okay, we have diamagnetic substance, this. Okay, so there are dipoles inside the magnetic substance. Okay, and they are randomly arranged, guys. Okay, these dipoles are randomly arranged in different directions, like this. Okay, in magnetic substance, in diamagnetic substance. Okay, and so now these are randomly arranged. Okay, those dipoles. So when we apply the magnetic field, okay, in the diamagnetic substance, so in that case, in presence of in presence of external magnetic field, dipoles dipoles are aligned, all the dipoles are aligned, okay, aligned, aligned, opposite, opposite to the, opposite to the, opposite to the direction of magnetic field, okay. So in diamagnetic substance, uh, so initially when there is no external magnetic field, all the dipoles inside the material, diamagnetic material, are randomly arranged as I have shown in the figure, okay. So as we apply the magnetic field on diamagnetic substance, means in presence of external magnetic field, all dipoles, okay, the dipoles are aligned opposite to the direction of magnetic field, okay. So I'll show you like this. So this is the diamagnetic substance, and we have applied the external magnetic field, okay, like this. The direction of this, okay, magnetic field direction is this. So these dipoles will arrange like this in the direction opposite to the direction of magnetic field, okay. So this is in presence of magnetic field. So you can see the direction of magnetic field and the direction of those dipoles are opposite to each other, right, and they are aligned in this way, okay, okay. So as I have explained this mu r, this relative in magnetic substance, in diamagnetic substance, relative permeability is equal to chi plus 1, okay. So where, since mu r equal to chi plus 1, very important formula, okay. So where mu r is relative permeability, relative permeability, relative permeability, okay, and chi is magnetic susceptibility, magnetic susceptibility, magnetic susceptibility, okay. Next is in this diamagnetic substances, the magnetic field lines never crosses the diamagnetic material, right. So I have explained that in Meissner effect, right. So this is diamagnetic substance, and the magnetic field line passes outside of the diamagnetic material, right. Inside the diamagnetic material, B is 0, right, B inside is 0. This I have explained in Meissner effect in my previous lecture of that superconductivity, okay. So magnetic field line, magnetic field lines never crosses, magnetic field lines never crosses diamagnetic material, okay. So magnetic field lines never crosses diamagnetic material, okay. Okay. Next point is, so magnetic susceptibility, that X is negative in diamagnetic, okay, in diamagnetic material, diamagnetic in diamagnetic material, okay. So if we talk about the perfect diamagnetic, okay, so for perfectly diamagnetic, for perfectly diamagnetic material, for perfectly diamagnetic material, the value of chi, the value of chi, the value of chi equal to -1. This is also important one. Okay, so this is exactly -1 for perfectly diamagnetic material. Okay, and the value of chi, is -m upon h. That is also I have explained in my previous lectures. Okay, so m upon h, where m is magnetization, m is magnetization, and h is magnetic field strength. Okay, or this is magnetic field, applied magnetic field. Okay, magnetic field intensity also we can say. Okay, so this is magnetic field. Okay, so chi equal to, very important formula, chi equal to -m upon h. Okay, next is, and for perfectly diamagnetic material, one more thing, mu r equal to 0. Okay, because we know mu r value is this, mu r is this one, right? Mu r equal to x plus chi plus 1, right? Chi is -1 for perfectly diamagnetic, so -1 plus 1 equal to 0, right? So for uh, perfectly diamagnetic material, mu r is 0, relative permeability, and here relative permeability mu r is equal to permeability of material upon permeability of vacuum, right? This one. Next is, this is also important one, for diamagnetic material, this chi dia, this value is, chi dia value is, this diamagnetic chi dia is, value of chi is, very important formula, you need to note down. Okay, so this is minus ZE square, n mu 0 upon 6m, this the average of r square. Okay, or root mean square. This is important formula, guys. This is chi dia equal to minus ZE square n mu 0 r square, this average of r square upon 6m. Okay, so where n is, capital N is number of atoms per unit volume. Okay, number of atoms per unit volume, number of atoms per unit volume. Okay, this is the n, and r square is average value of, important, average value of r square over a particular orbit, over a particular okay, so n is number of atoms per unit volume, and r square is average value of r square over a particular orbit. Okay, and this one, and this is the orbit is that electrons moves, right, in the atom, because electrons moves around the nucleus, right? So average value of r square over a particular orbit. Okay, and if you draw the graph chi versus t for diamagnetic, so this is going to be like this graph, chi versus t temperature, this is going to be like this. This is the graph. Okay, constant value. This is the graph. This is the graph. Okay. This is the graph between chi versus temperature of chi is the magnetic susceptibility of diamagnetic material. Okay, substance. Next, guys, since we know that I, that is, I'm talking about I current. Current is Q upon T, right? Q upon T, and so if we talk about electron moves around the orbit, right? So in that case, this is going to be, this is Q charge. Okay, charge Q upon T, right? So this is going to be minus E, charge is E upon T, or that is the time period, right? E upon T, and or we can write minus E upon T, time period of completing uh, one completing one circle. Okay, so here this one T, and value of T we know, right? This is minus E upon 2 pi upon omega, since value of T is 2 pi upon omega, right? And we can write I value, that current is going to be this one, minus E upon 2 pi EB upon 2m, minus E upon 2 pi EB upon 2m, right? First we'll write this minus E upon 2 pi omega, and omega value is, this is important, omega value is this one, QB upon 2m, QB, that is charge upon 2m, right? And this is for this is also called Larmor frequency. Okay, Larmor frequency, and for our omega value is QB upon m, that is for cyclotron frequency. Okay, cyclotron frequency. This is an important point. Okay, so for last, so here the value of omega will write, that is I is going to be minus E upon 2 pi, and this is QB upon 2m, or Q we can write electron, right? E, charge EB upon 2m. We can write that EB upon 2m. Same thing. Okay, EB upon 2m. EB upon. So we'll solve it further. So here, so I is now, this is minus E square B upon 4 pi m. So this is the current. Okay, I, E square upon B, this one. Okay, E square minus E square B upon 4 pi m, right? And now we know we are finding magnetic moment. Okay, so magnetic moment, the magnetic moment is going to be magnetic moment formula, that is mu m, that is we know, right? Magnetic moment is current into area. You need to note down. Okay, this is the magnetic moment, current into area, right? So mu m is going to be current I, this we have, right? This is minus E square B upon 4 pi m. Okay, into area we know, right? That is for this area is going to be pi into average of P square. Okay, so where P square is mean square radius, right? Mean square radius. P square is mean square radius. So from here, we can write now, since we have this r square is value of r square is average value of x square plus average value of y square plus average value of z square. Okay, and from here the value of p square is going to be 2 by 3 mean square value of r. Okay, mean square value of r. And so from here the magnetic moment is going to be magnetic moment mu m is going to be minus z e square b. This is for this is for hydrogen atom. Okay, so for any other atom there is a z equal, for hydrogen atom z equal to 1. So here this is going to be z e square b. It's a general case, so minus z e square b r square average upon 4m. This is important formula. So this is the magnetic moment for diamagnetic material. Okay, mu m is minus z square eb upon 4m into mean square radius, that is minus z e square b upon 4m into average of r square or mean square of radius. Okay, this one. So from here you can see this mu m is proportional to mean square radius. Magnetic moment is proportional to mean square radius. And also x dia is proportional to mean square radius. I have already found this, explained this one, right? X dia value is this. So here also minus z square n mu 0 r square mean square of r upon 6m, right? So x dia is proportional to mean square radius, and also mu m is proportional to this mean square radius. Okay, so from here we can conclude like that the outermost electron, right, because it's depending upon r, right? So the outermost electron makes largest contribution outermost electron makes largest contribution in the magnetic moment mu m and chi, that is magnetic, I can write magnetic susceptibility. Magnetic susceptibility okay, or magnetic susceptibility chi. Okay, so outermost electrons makes largest contribution in the magnetic moment mu m and magnetic susceptibility for diamagnetic. Okay, well, and next is for diamagnetic substance x is minus m upon h, guys, right? And that is equal to that minus m upon s, magnetization upon magnetic field strength, and that is equal to minus z e square n mu 0 upon 6m average of R square. Okay, this is important one. Okay, this one. So these are the values of chi, magnetic susceptibility for diamagnetic material. Okay, I hope guys you have understood it. Next is paramagnetic material. Okay, paramagnetic material. Paramagnetic material. Okay, so in absence of magnetic field, so in paramagnetic substance, also in absence of magnetic field, dipoles are randomly arranged. Okay, so in absence of in absence in absence of magnetic field, in absence of magnetic field, the dipoles are randomly arranged. Okay, dipoles are randomly arranged. So like this is the paramagnetic substance. Okay, and there is no magnetic field, right? Dipoles are randomly arranged like this, similar to diamagnetic substance. Okay, now in presence of magnetic field, in presence of magnetic field, this is substance and this is the magnetic field now. Okay, in presence of magnetic field. Okay, external magnetic field. In present of external magnetic field, or I can write the external. So in presence of external magnetic field, dipoles are arranged in the same direction as the external magnetic field. Okay, so the direction of dipole moment and the direction of external magnetic field is same. So if we talk about this diamagnetic substance, the direction of magnetic field and direction of dipoles are in opposite direction, right? But if we talk about paramagnetic substance, you can see in presence of external magnetic field, the the direction of direction of dipoles and the direction of magnetic field lines are same, in the same direction. Okay, so this is the in presence of magnetic field. Okay, next guys, very important thing. So if temperature is increased, okay, in case of paramagnetic substance, if we increase the temperature, okay, so that implies the magnetic susceptibility chi decreases. Okay, due to thermal agitation, due to thermal agitation. Okay, so if we in paramagnetic substance, if we increase the temperature, right, the chi will decrease due to thermal agitation. So it means chi is proportional to T. My apologies, it's 1 upon T. Chi is inversely proportional to P, or chi is proportional to 1 upon T. Very important. Okay, or we can write here chi is equal to C upon T. Very important formula guys, you need to note down. chi equal to C upon T. Okay. Chi equal to C upon T, where C is Curie constant, guys. Okay, where C is Curie constant. Curie constant. Okay, where C is Curie constant. Okay, so this is important formula, guys. You need to know for paramagnetic substance, chi is equal to C by T. Okay, and if you draw the graph between temperature versus the chi for paramagnetic substance, the graph is going to be like this. Okay, this is the graph. And also if we draw the graph between temperature and 1 upon chi, chi is the magnetic susceptibility of paramagnetic substance, right? Then we are going to get this graph going from origin. Okay, this straight graph going from origin, this one. These graphs are important, guys. Okay, they are asked in the examinations. Okay, so this is the two different graphs. One is chi versus temperature and another is 1 upon chi versus temperature for paramagnetic substances. Okay, next is saturated magnetization. What is saturated magnetization? Okay, saturated magnetization. Saturated magnetization. Saturated magnetization. Saturated magnetization. What is saturated magnetization? And this is denoted by MS. Okay, so in case of this paramagnetic substance, when we increase external magnetic field, so magnetization will get increased. Magnetization will also increase, but after some time, when all dipoles get aligned parallel to the external magnetic field, get aligned parallel to external magnetic field, external magnetic field, then saturation will occur. Saturation will occur, and magnetization becomes constant. Magnetization becomes constant. Okay, so here, guys, what will happen is they are randomly oriented, right? So if we put this paramagnetic substance in dipoles are randomly oriented, right? If you put this paramagnetic substance in the magnetic field, these dipoles will align themselves parallel to the magnetic field, and the direction will be the same, right? Same as the magnetic field. So they will so what will happen is initially when they will align, they start aligning themselves parallel to the magnetic field. That time the magnetic field will also increases, right? But after some time they all will get aligned. All dipoles will get aligned in the same get aligned parallel to the magnetic field in the same direction. After that, the magnetic field, that magnetization is going to be saturated, and then that has constant value, right? That's what it is said. Okay, so when we increase the external field initially, that time magnetic field will get increases. Okay, and but after some time, when all dipoles get parallel to the external magnetic field, then saturation will occur and magnetization will become constant. Okay, so graphically we can represent it like this: the graph between M versus H, magnetic field intensity versus M. Okay, so what will happen when we increase the magnetic field? This will also increase. Okay, but after some time this will be constant when all the dipoles are aligned in the same direction, parallel to the magnetic field in the same direction, right? So this is the graphical representation of saturated magnetization. Okay, I hope guys you have understood it. Next point. Okay, so next is, so we have this for paramagnetic, we know chi equal to C upon T, right, where C is the Curie temperature, right? And guys, this is important, chi equal to C upon T. Okay, and the value of C, value of C is very important, mu 0 mu square n upon 3k, very important. Okay, so we can derive it by quantum theory as well as classical theory. So you need to know this value, guys. Okay, questions will be asked based on this formula. Okay, so this is C equal to uh, mu 0 mu square n, mu 0 into mu square into n upon 3k. Okay, where mu 0 is permeability of free space, mu is permeability of paramagnetic substance, and is the number of atoms per unit volume, and k is the Boltzmann constant. Okay, so here, so if you put the value, then chi is going to be, chi value is going to be, mu 0 mu square n upon 3 kg. Okay, very important. For this value is very important. The value of this is Curie constant. Okay, this is called Curie constant. Curie constant. Curie constant, and here I'll write all this. Mu is permeability, permeability, permeability of free space or vacuum, free space. Mu is permeability, permeability of substance, that is paramagnetic substance. Substance, and n is number of atoms per unit volume. Okay, and k is the Boltzmann constant. Boltzmann constant. K is the Boltzmann constant. So this is important. Okay. Okay. So these are important things about paramagnetism or paramagnetic substance. Okay, paramagnetic material. Next is ferromagnetic material. Okay, uh, ferromagnetic material. Ferromagnetic material. Ferromagnetic material. Okay, so I'll show you. So in absence of external magnetic field, they also behave as a magnet, guys. Okay. So in absence of in absence of external magnetic field, external magnetic in absence of external magnetic field, external magnetic field, they also they behave as a magnet. Okay, they means ferromagnetic material. Okay, they behave as magnet, as a magnet. Okay, so in absence of external magnetic field, they behave as a magnet. Okay, still if there is no magnetic field, still they behave as a magnet. Okay, so they are directed like this. Okay, so you can see there the orientation of dipoles inside the material are as I'm going to show you. Okay, so like this. So net dipole moment is not zero here, right? So that's why. So they are arranged in ferromagnetic material. The dipoles are arranged in this fashion. Okay, and the net dipole moment is not zero, guys, and that's why in absence of magnetic field they behave as a magnet. Okay, so this is the diamagnetic. This is a ferromagnetic material. Okay, so the orientation of dipoles are in this fashion, and the net dipole is not zero. Dipole moment is not zero, right? And that's why they behave as a magnet. Okay, even in absence of external magnetic field, they behave as a magnet. Okay, because their dipole moment is not zero. Okay, so this is the orientation of dipoles inside the ferromagnetic material. Okay. So in presence of magnetic field, next, in presence of magnetic field, okay, in presence of magnetic field, the dipole will arranged in the same direction as magnetic field. Okay, in the so dipole will arranged themselves parallel to the magnetic field in the same direction. Okay, so this is the magnetic field. Okay, so this is in presence of magnetic field. In presence of magnetic field. In presence of magnetic field. Okay, so in presence of magnetic field. Now here the magnetic field will be, there would be strong magnetic field, guys. Okay, because strong, so they will behave as a strong magnet. Okay, strong magnetic field, strong magnetic field, because without in absence of magnetic field, they are behaving like magnet. So in presence of magnetic field, their intensity of magnetic field get increased. Okay, they are strong magnetic, so they would be strong magnetic field, or they are strong magnet. Okay, this one. Next point, ferromagnetic property exists. Ferromagnetic property, ferromagnetic property exists only, very important point. Okay, only below a certain temperature, below a certain temperature. Okay, so ferromagnetic property exists only below a certain temperature. Okay, so they would, so there is a certain temperature below which the paramagnetic substance will behave as a ferromagnetic material. Okay, so ferromagnetic property exists only below a certain temperature. Okay, called Curie temperature. Okay, called Curie temperature. Curie, and that temperature is called Curie temperature. So ferromagnetism will exist below a Curie temperature. Okay, so here the value or the magnetic susceptibility, that is chi, for the ferromagnetic material is C upon T minus Tc. Okay, this is important formula, guys. You need to note down. Okay, C upon T minus Tc. Okay, C upon T minus Tc. This is also called Curie-Weiss law. Okay, Curie Curie-Weiss law. Curie Curie-Weiss law. This is also called Curie-Weiss law. Okay, this is also called Curie-Weiss law. And Curie-Weiss law is a very important formula, guys. You need to note down. And here, guys, this one, M upon the magnetization at temperature T Kelvin upon that saturated magnetization at 0 Kelvin, that is equal to KTX upon n lambda mu 0 mu square. Okay, so where x value is mu b upon kt. Okay, mu b upon kt. B's magnetic field will be uh, this one, permeability. Okay, n is the number of atoms per unit volume, and x value is this, and this value we know, right? So this is magnetization. Okay, this is important temperature value. And also, guys, here Tc, I'll write in next page. Value of Tc is lambda c. Okay, where where lambda value is Weiss coefficient. Okay, Weiss coefficient. So this lambda value is Weiss coefficient. Okay, Weiss coefficient. It is also important value of Weiss coefficient. Okay, and here value of magnetization, that M is going to be n mu bx, magnetic field which is function of x. Okay, or we can write M value is mu n mu, we put bx value, so n mu 10 hyperbolic mu b upon kt, 10 hyperbolic mu b upon kt. Okay, so this is m equal to n, right? This one. Okay, now next point, that is very important point. So ferromagnet, so this one, ferromagnetism to paramagnetism. Okay, ferromagnetism to paramagnetism, PM. Okay, or paramagnetism to ferromagnetism. This is the second order phase transition, guys. Okay, second order. I have already explained first order phase transition and second order phase transition in thermodynamics and statistical mechanics lecture. Okay, so second order phase transition. Okay, so this is so Fm. So ferromagnet becomes paramagnet, and paramagnet material becomes ferromagnetic material. Okay, this is the second order phase transition, guys. Okay, now Weiss constant, guys. So there is a Weiss constant. Weiss constant. Weiss constant value is, that is lambda. Lambda is Weiss constant or Weiss coefficient. That value is 3 kT, 3 kTc at Curie temperature. Okay, this one 3 kTc Tc upon n mu 0 g square mu square j into j plus 1. Okay, so this is also important. So here this one. Okay, this point also you need to note down that at T is greater or equal to Tc, Fm converts into Pm, paramagnetic substance. Okay, so this is Fm to paramagnetic, paramagnetic to ferromagnetic. This is second order phase transition, and this is the Weiss constant lambda value 3 k Tc mu n mu 0 g square mu square j into j plus 1. Okay, j is quantum number and mu is this mu is, we know, right? This is this magnetic moment of the material. Okay, next is we can write, because we have this formula right now, chi equal to c upon t minus tc, right? We have this formula. So now we can write 1 upon chi. If we do like this, 1 upon chi is t minus tc, t minus tc upon c, or we can write 1 upon chi is going to be t upon tc, t upon tc minus tc upon c. This is also important. Okay, 1 upon chi equal to t upon tc minus tc upon c. Okay, next is, so if you draw the graph, very important graph, this is chi versus temperature. Okay, this is 1 upon chi, 1 upon chi, this is chi, guys, not x. Okay, 1 upon chi versus temperature. If we draw the graph, so graph is going to be like this. Okay, this one, this is the graph, guys. Okay, this is a straight line, guys. Okay, this is graph, this is at tc, and this is tc upon c. Okay, this is the Curie temperature, right? This is the Curie constant, this one. Curie-Weiss law. Okay, so this is the one, guys. So this is the straight line graph, and you need to know that this is very important graph. So 1 upon chi versus temperature. This is the case of ferromagnetic material. Okay, ferromagnetism. So this will be the graph, will passes through here. Okay, this one. So this is the graph, temperature versus 1 upon chi. Okay, one more point. Here, guys, this one. Okay, so this is the Curie temperature. Okay, Tc. Okay, so below this temperature, substance will be ferromagnetic, and above this temperature substance will be paramagnetic. Okay. Next, guys, I'm going to tell you one trick. Okay, so this will help you to solve the question. Okay, so this is a line. Okay, this is TC temperature. Okay, this is below TC. Okay, and this is above TC. Okay, so here T is less equal to TC, and here T is greater equal to TC. This is Curie temperature. Okay, so here this is a formula you need to note down, guys. This is a trick. Okay, actually trick. If this is the case, okay, so if TC is TC is greater than T. Okay, if TC is greater than T, then the M is going to be proportional to TC is greater than. Okay, TC greater means TC minus T to the power half. Okay, and the second is if this is TC greater than T. Okay, this is the case. Next is M is proportional to, in this case T is greater than TC. Okay, so T minus TC, and this power is going to be minus 1. This is T greater than TC. This trick you need to know. This mass, this M is proportional to TC minus T to the power half if TC is greater than. Okay, and M proportional to T minus TC to the power minus 1 if T is greater than TC. Okay, this one. This is the trick you need to note down. Okay. Next is antiferromagnetic 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 material antiferromagnetic material. Okay, antiferromagnetic material. So here you need to understand this. Okay, the dipoles are in this antiferromagnetism are arranged in this way. Okay, so in this way, and so here net magnetization is 0. Okay, because net, they will cancel each other. Okay, net magnetization net magnetization net magnetization is 0. Net magnetization is 0. Okay, so because they have equal magnitude and opposite direction. Okay, so because in case of antiferromagnetic material, the net magnetization is 0, guys. Okay, because they have equal magnitude, and the dipole have equal magnitude, equal and opposite. They have equal magnitude, and they are in opposite direction. Okay, equal magnitude and opposite direction. Okay, for antiferromagnetic material, the value of chi, that is magnetic susceptibility, is going to be 2c upon T plus Tn. Okay, this is important formula. T plus Tn. That chi equal to 2c upon T plus Tn. Where Tn is, this is a new thing. This is a Néel temperature, guys. Okay, this is a Tn is Néel temperature. Okay, this is the formula for antiferromagnetic material. Okay, well, now in case of this one, if we draw the graph, okay, draw the graph for antiferromagnetic I'm talking about. If you draw the graph, that is T versus 1 upon chi. So this is going to be like this. This graph is going to be the straight line like this. Okay, this is a straight line, guys. Okay, so this is minus Tn. This is Néel temperature. Okay, minus Tn. and this value is Tn upon 2c. Okay, so this is Néel temperature. This is a graph, the temperature versus chi for antiferromagnetic. Okay, so ferromagnetic, you can see graph, this one. This goes from here. Okay, and this is for this one. This is the for antiferromagnetic. This is Tc temperature, right? This passes from there at critical temperature, and if you talk about this antiferromagnetic, this passes from Néel temperature Tn. Okay, Néel temperature, and that is the minus value, minus Tn. Okay, this is the graph, and also we can write 1 upon chi, because we have this formula chi equal to this 2c upon t plus Tn. So we can just, so what we can do is we can just we can do like this. 1 upon chi equal to 1 upon chi is going to be t plus Tn upon 2c, and that value is going to be t upon tc, t upon 2c plus Tn upon 2c, t upon 2c plus Tn upon 2c. Okay, okay, next is ferrimagnetic material. Okay, ferrimagnetic material. Ferrimagnetic material. Okay, ferrimagnetic material, this is going to be this one. Okay, here the net magnetization is not 0. Okay, net magnetization not equal to 0 in case of ferrimagnetic material. Okay, net magnetization is not equal to 0. So this is so there is one question, guys, which is asked in TIFR and GATE. Okay, so question is asked in TIFR 2013 and GATE 2021. Okay, this question is asked. Okay, so the question is simple. This is graph. So we have to select the correct graph. Okay, so here this one, this line passes through here, and this line passes through there, and this line passes through there. Okay, so this is the graph given. So this graph is A, B, and C. Okay, so guys, this is for this graph. The line which passes through magnetic field passes through the origin. This graph is for PM, that is paramagnetic substance. Okay, and above this graph, this line which is this is A, above this graph, above this paramagnetic graph, this line is for antiferromagnetic material. Okay, and this graph is for ferromagnetic material. Okay, so this question is asked, guys. Okay, so I'm writing directly the answer. Okay, so these three graphs are given. Okay, and we need to choose which graph is for which material. Okay, so the graph, the line which is passing through the origin is the graph for paramagnetic substance. Okay, and this line above this paramagnetic line is the graph for antiferromagnetic material, and this line which is below the paramagnetic material line is the graph for ferromagnetic material. Okay, so very important. And here, guys, one more thing, that is, so if you draw the graph for this graph for T versus for this for antiferromagnetic I'm talking about. Okay, T versus chi. Okay, so this graph is going to be like this, antiferromagnetic and paramagnetic, like this. Okay, this is Neal temperature, okay, Tn, and this is chi, magnetic susceptibility, and this is temperature. Okay, this graph is so we have to identify this graph. Okay, so this graph is for antiferromagnetic material, AFM, antiferromagnetic material, and this graph is for paramagnetic material. Okay, and here this T is less than Tn, obviously, and here T is greater than Tn, that's Neal temperature. Okay, this is also important. So this graph is this is the graph that chi versus T. Okay, and this line represents the antiferromagnetic material, and this line represents the paramagnetic material, and this is the uh, Neal temperature. Okay, so below Neal temperature there is an antiferromagnetic material, and above Neal temperature there is a paramagnetic material. PM is paramagnetic, AFM is antiferromagnetic. Okay. Okay, guys. So I'm going to stop here. So, guys, just wanted to tell you that I have completed the condensed matter physics in 22 lectures now. Okay, so I would request you, and that is available in my playlist. So I would request you, please watch. I have completed many courses, and for that you need to check my playlist. So I would request you guys, please watch my free live lectures in the playlist. Okay, and also watch my free live classes, which are going to help you to crack the exams related to physical science. And also, guys, please subscribe my channel, and also, guys, share my lecture details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, okay, guys, thank you so much. Bye now.